Okay, here we are. We're going to start talking about the chain rule, which we started talking about in the last video, but now we're going to really hammer this home. And this is video 11. I think we're in week 6, and it's Wednesday the 23rd. So the point here is that whether or not the chain rule is in R1, R2, R3, or Rn, it works. So let's let x be some function whose independent variable is t, and y is another function whose independent variable is t, and assume they're both differentiable at all t. Then the function z equals f of xy is differentiable at some point xy, and the derivative with respect to t of z is dz dx partial times dx dt regular plus dz dy partial times dy dt regular. I don't think that's right. Something's wrong here. Let me fix this. It's supposed to be an eraser. So what we're doing is we're taking an ordinary derivative with respect to t of z. And let me get some color in here to make this clear. So this is a partial. And this is a partial. That should be dz dy. So it's the ordinary derivative with respect to t of z is the partial with respect to x of z times dx dt regular plus the partial. I have an eraser. With respect to y of z times regular dy dt. Okay. So the chain rule works, but you have to inculcate the partials because we're working in 3 space. All right. So let's look at an example here. We're going to let z be the function x squared y, so that's my f of xy. X of t is t squared, and y of t is t cubed. And we want to compute dz dt. Okay, so this is going to be, I'm just going to use this equation up here. dz dx is 2xy times dx dt is 2t plus dz dy is x squared times dy dt, which is 3t squared. Okay. Well, it's important to note that we're looking for dz dt, so there shouldn't be any x's and y's around there. So we clean this up. This is 2 times x, which is t squared, times y, which is t cubed, times 2t, plus x squared, which is t squared squared times 3t squared, and this becomes 4t to the 6th, 2 plus 3 plus 1, plus 3t to the 6th, which is 7t to the 6th. Okay. And now we have dz dt in terms of t, and all the x's and y's are gone. Okay, and so we had to do a little bit of back substituting there, which is what you do with the chain rule in general, but we don't really talk about it that way. All right, so let's look at a application example here. Do some writing. At what rate is the area of a rectangle changing if its length is 15 feet and increasing at 3 feet per second, and the width is 6 feet, and increasing at 2 feet per second. Right? So we're looking for what? We're looking for dA dt. So we want dA dt. That's our mission. All right, let's draw a picture here. I'm going to let x be the length and y be the width. All right, just to define variables here. And these are both increasing at 15 or 3 feet per second and 2 feet per second respectively. And during this model, we're stopping at 15 and 6. Okay, so all right, well, what's the equation? Area, which is a function of x and y, equals x times y, given this length and this height, or this length and this width. Okay, and x and y are functions of t. Okay, so we want dA dt, which is d partial dx times dx dt plus d partial dy times dy dt. Okay, the partial with respect to x of xy is y, and dx dt is 3, that's given. dA dy is x, and dy dt is 2. Okay, and so we're evaluating this at the point 15, 6, because those are the given, and we get 18 plus plus 30. And so the rate is 48 feet squared per second. So there you go. It's just like Calc 1, only x and y are both changing. Okay. So let's keep going with this. Just to show you how cool the chain rule is. And once you get this second example, you can apply this to any number of variables, right? So we're gonna let z equal a function of x and y, but this time, no, sorry, I'm one off. We're going to let w be a function of x, y, and z. So now we're in 4 space, but that's all right. Each one of these x, y's, and z's are going to be, they're going to be functions of 2 parameters. So x is a function of s and t, y is a function of s and t, and z is a function of s and t. Okay, and so now all we can look at is, all we can consider is, so now we want to compute dw dt partial, because we can't now say just dw dt. Okay, well, you just do what comes naturally. You go dw dx times dx dt plus dw dy times dy dt plus dw dz times dz dt. And the important thing to note here is that once you go into this realm, you see that x is a x, y, and z. So x is a function of 2 parameters. So you can't just take x prime. Before you could, because x was just a function of 1 variable, and you took x prime, it was x prime of t. So now you can only take partials, so all of these are partials. Okay. So I'm going to give you some guided practice here, so that when you guys come online, we'll start talking about these 2 problems. I got 2. So problem 1, we're going to let z be x squared plus y squared. This is a paraboloid. X is cos t, y is sine t, and you want to compute dz dt at t equals pi. So that's problem 1. And problem 2, z equals tan inverse of x over y. X is going to be equal to u cos v, and y is going to be u sine v. and we want to compute dz du partials and dz dv partial at at 1.3 comma pi over 6. So that's the point uv. Okay, I'll see you all in a minute.